Okay, so I hope yesterday's session was, I hope it was well understood. Even though I know that I don't expect that you grasp everything that was said yesterday, but at least to a good extent, um, you all were able to pick up something from the training. Perhaps when you now on your own time go through the material, you should be able to gain a full understanding of what it's all about. So today is going to be an interesting one. We're going to talk about solar PV design and sizing. So today I will take you through all the whole processes of determining or calculating the size of required inverter, battery size, PV panels, charge controller. I'm going to walk you through all the calculations, and I will please ask that if you have a scientific calculator, you might want to just bring it closer to you because you might be using it. If not, you can use your phone or any other calculator. It mustn't be scientific anyway because I don't think we have much scientific formulas to use. But it's good you have a calculator handy while we go through this process. As we proceed, there'll be some exercises that I'll be requesting that you all complete and then share your results so that we can all um, assess the level of our understanding. So having said that, we have to proceed now. So like I said, we'll be talking about solar PV design, sizing, and basically we're going to be doing some calculations. So yesterday, I thought that one of the most important things that you need to know as a solar PV designer or developer is the load that you want to power, the load that you want to provide electricity to power. So if you don't have an idea of the load, then you're almost blind in what you're doing. So to be able to determine the energy requirement for the load that you need to power, you have to do a simple load assessment. Okay. So what you're looking at the screen now is a table that has a sample electrical load detail. So this is just a sample. So if you, for example, you go to an apartment and you can find a television in that apartment, you can find a fridge, you can find light bulbs. Okay, perhaps they have 4 televisions, they have 1 fridge, and they have eight bulbs and 1 standing fan. This is just an example. The list, of course, could be more, but I'm just using this as an example. And again, you have to take notice that if you go to an apartment, you have to ask, or if not an apartment, whatever load that it is that you want to power, you need to ask your client, you need to ask him to list the items or the appliances that he needs to power. So it mustn't be that the client must power everything in the house or in the facility with this solar system, considering the cost. Okay, so the only thing that you might take into consideration here are the load that needs to be powered by this solar system, okay, and not necessarily the whole load in the house. So for me, the sample that I have here, this client wants to power his television, and he has 4 televisions. So, and he has a fridge, he has 8 light bulbs, lighting points, and he has a standing fan that he wants to power. Okay, so when you look at the ratings, all of these appliances has their energy rating, their power consumption rating, okay? So when you look at the appliances, you look at the ratings in terms of their power, not energy this time, their power, which is in wattage. So the TV, each of them are rated 50 watts, 50 watts for each of them. And then the fridge is rated 150 watts. The light bulbs, each of them is rated 15 watts, and then the standing fan is rated 40 watts. If you add all of that together, you're going to get 255 watts. So that is the demand that you're designing for you. So you're designing to meet a demand of 255 watts, assuming that all of these appliances are running at the same time. Okay, assuming that all the appliances are running at the same time. So your design should be able to support a load of 255 watts. Okay, now that is power. You need to also establish the energy requirement, the amount of energy required to power this appliances. So how do you do that? You have to ask how many hours of usage for each of these appliances. So for television, how many hours is this client going to use it? So you want to design a system that can support the operations of that television for 6 hours. You want to design a system that can support the operation of the fridge for 12 hours. And the system should also be able to support the use of the light bulb for 8 hours, and then the standing fan for 1 hour. Okay. So when you now calculate the energy requirement for each of these appliances or this equipment, so for the television, you have 1,200 watt hour in a day. For the fridge, you have 1,800 watt hour in a day. And then for the light bulb, for the 8 of the light bulbs, you have 960 watt hour. And of course, the standing fan, you have 40 watt hour. So when you add all the watt hour, you have 4,000 watt hour. Now, remember I told you that power and energy are different. Now, this 4,000 is energy, okay? And this 255 is the power. This power is very, very important when you're sizing your inverter, okay? Assuming you want to rate your generator, you want to buy a generator. So the inverter serves the same purpose as your generator, just it's synonymous, not exactly the same thing, but it's synonymous to your generator. So the same way you size your generator is almost the same way you size your inverter. And that's why we are looking at the demand here to size our inverter, okay? Then this energy that we are looking at here is very important to be able to establish the battery, assuming that we're going to have a battery storage, okay? Then you need to know the amount of energy that you need to support the operations of all of this equipment for this number of hours in a day. So that will enable you to determine in a day the amount of energy that you need to support that house or your client. So this is a simple load detail or a simple energy assessment, or you can as well call it a basic energy audit. Okay, so it's very, very important that this is the first step in any solar system design. The first step is to assess what needs to be powered, the load. You need to do a simple energy audit, and it's very, very important that we learn how to do this things. Okay, so there's an Excel sheet, Excel file that I think Uche has shared it. If he hasn't, it will be sent to you, where you can do this load assessment, on Excel. All you need to do, put the number of television or put the name of the appliances, put the quantity, then put the power rating and the hours of usage. This energy requirement will be calculated automatically. So we'll share that file with you. There are some other things in that Excel file that you find useful. So this is a simple energy audit or load assessment of the facility that we need to power. So now, let us, like I said, the inverter is synonymous to your generator. So let us determine the size of inverter that we're going to need to power this. The size of inverter that we are going to need to power these appliances. Okay. So now, the peak demand that we need to power is 255 watts. Okay. So, but of course, we know that inverters are rated in kVA or VA. kVA is the same thing as VA, but only that in kVA, you're now dividing by 1,000, okay? So when you're rating inverters, you will often hear kVA or VA if they are smaller size. Therefore, assuming that a power factor of 80%, okay? Now, when you're rating your generator as well, your generator is rated in kVA, but that does not mean that kVA is the actual output. The actual output will now be determined when you now take the power factor into consideration. Then the actual energy that will come out from that generator will be less than the rated kVA, and that same thing applies for inverter here. So assuming that our power factor for this inverter is 80%, and our desired load factor is 70%. Now, why 70%? We want to create some level of tolerance in this inverter so that if, for example, the load at some point now exceeds 255 watts, the inverter should be able to accept, just for those little margins. So our design, we're designing that this inverter is, the load factor for this inverter is 70%. So that if there is additional load, it can be able to withstand it, just slightly. So inverter size here would be the peak demand divided by the power factor times the load factor. I take that again. The size of our inverter here will be the peak demand, which is 255. You have to divide it by the power factor, which is 0.8, times your load factor, which is 0.7. Okay. So when we do that, we will now find out that our required inverter size will now become 455.36 VA. In other words, this can be 0.45536 kVA. So let us be clear on this. Let us not confuse it. If you see VA or kVA, they mean apparent power. For those of you that attended the first training, I'm sure this should be clear to you. It shouldn't be confusing to you. There are different kinds of power. You have apparent power, then you have the real power. Okay, so you need a power factor to convert apparent power into a real power. Okay, so when we are sizing inverters are rated in apparent power. Okay, like I said, it's similar to your generator that are being sized in kVA. So for this load of 255 watts, this is the size of inverter that we need, so that, and this inverter, we want to load it, we want a load factor to be 70%. So you have 30% tolerance level. If this inverter can actually take more than 255 watts, okay, based on the load factor that we have used in our calculations. So this is how you size your inverter. It's a basic calculation, and it's straightforward. It's simple and it's straightforward. The only thing that you need to know is that you need to take into account your power factor, which in most cases is 0.8 or 0.9, depending, and then your load factor. Load factor is just a margin. Okay, it's just kind of a safety margin, so that your inverter does not blow up. The problem is, if you choose to put 100%, if you decide to remove this 0.7 and you design for this 255 watts, if the load eventually exceeds this 255, then there could be a problem. So that's why we need to determine what our load factor would be, and it must be less than 100, so that we can be able to have that safety margin. So let's proceed. So our first exercise. So the exercise is this: calculate the inverter size required if the peak demand is 400 watts. In the explanation that I just gave, our peak demand is 255. So I'm not asking you to please calculate what inverter size that we are going to require, assuming our peak demand is now 400 watts, and the power factor is 75%, and the desired load factor is 60%. Now, the reason why we decide to, in this example, now in this exercise, part of the reason why we decide to use 60% is that this client wants to add additional load in the future. So he's now saying, okay, use 60% in your load factor for this inverter, so that in future I can be able to add additional load. Maybe then that time the load factor can now increase to 70 or 80%. And that is the reason why you choose to design with 60% load factor. So please, can you just test your skills on this, and let me see what results you get. You can unmute yourself and speak to the mic if you want to speak, or you can type it in the chat box.
0.784 kVA.
0.784 kVA. Okay. Let me wait for other people to also respond. I don't know if anybody has posted anything on the chat.
I've posted mine before he talked.
Okay.
0.784.
Okay. So
kVA.
Okay, correct. So we all got it correct. the size of the inverter required to support this load of 400 watts at 85% power factor and a desired load factor of 68.784 kVA. Correct. If you have it in VA, then you have 784 VA. They're all correct. So that's good. So let us look at sizing of the battery now. Now, from our previous, from our load assessment, the load that we need to support is 4,000 watts hour per day in a single day, 4,000 watt hour in a single day. So that's what we are also working on here. So your daily energy need, did someone raise hand? Okay, someone raised hand.
Okay, yes. I have a question to ask. Could you kindly go back to the last slide?
Okay.
Okay, now in this exercise number 1, you were talking about a customer who wants his load factor, or what have you, to be 60%.
Okay.
The question is this. Now, the reason for doing this is that the load factor may increase if his load demand is going to increase in the future, correct?
Correct.
Okay, so how about if we say, okay, if we just go ahead and design it with, say, 70 or 75 to still accommodate the load requirements that he is going to add after this time? I mean, is it going to make any difference? Is it that we will be giving him an inverter that is too big right now? So yeah.
Okay. So thank you very much for the question. Now, on a normal circumstance, on a normal condition, I would advise that you use 70% for your load factor when you're designing, or 80%. Okay. Yeah, but in this case, the client has specifically requested that you reduce. I mean, you give more safety margin because maybe he has planned to buy an additional appliances in the nearest future, not a distant time. Okay. So because of that, he doesn't want you to under design so that okay, so for example, this client already know that maybe in the next month or in the next 2 months, he's going to add additional loads to this your design. And then imagine you now design with 70%, okay, imagine you design with 80%, and you don't know about this information, and you design with 80%. If that client eventually add that load in the nearest future, then he'll be getting closer to 100%. And if there is any excess load or there's any offshoot in his consumption, it's going to damage that equipment or the inverter. Okay. Exactly. So in this case, the client is giving you a prior information that, look, maybe in the next month or in the next 2 months, I want to add additional load. So reduce the load factor from what I currently have now, so that when I add that additional load, the load factor can now stabilize. They can now come up to 70 or 80%. Is that clear?
Okay.
All right. Thank you. So back to the battery sizing that we were on. Can you mute yourself now that you finish asking your question? Okay. So we are still working with a daily energy need of 4,000 watt hour or 4 kilowatt hour, whichever one is correct. So now when we're designing, we also need to take into account that there could be a day. In fact, it's normal. It's usually there are usually days when there is no sun. There are usually cloudy days. You don't have sun. You could have rain all through the day, and in those cases, your solar panel might not be able to generate energy or power to charge your batteries. So when you're designing, there's what we call days of autonomy. So those are the days where you don't have any sunshine. Okay. So sometimes you have to now ask your clients how many days of autonomy does he or she require. Okay, so in this example now, I'm assuming that, okay, we want to design with 3 days of autonomy. So if there is no sun for complete 3 days, the storage in the battery should be able to last that client for those 3 days until the 4th day when the sun comes out. So that's what days of autonomy is. And in this case, I'm assuming 3 days. Now, this can vary. It can be 1 day, it can be 2 days, okay? Depending on your client specification, on what your client wants, okay? So, but it's good we also take this into consideration when we're designing. So your daily energy need plus 3 days of backup autonomy for non-sunny days. If you now do that, you now multiply your energy need by 3. So you're going to have like 12,000 watt hour. So if you want to do a backup that can be able to withstand 3 days of no sunshine, then you have to be designing for 12,000 watts hour. So that's what days of autonomy is. It varies. It can be 1 day, it can be 2 days, it can be 10 days, depending on what the clients want. Okay. So, however, this 12,000 watt hour is the usable size, okay, of the battery capacity. Okay. So for battery, that's what we call depth of discharge. I don't know if for some of you, if this is the first time you're hearing about depth of discharge. So for the benefit of those who are not familiar with depth of discharge, I'm just going to do a brief explanation. When you charge the battery up to 100%, okay, it's not always advisable for you to discharge it 100%. If you discharge it 100%, in most cases, the battery, in fact, you damage that battery. Okay, it becomes difficult for it to pick up and then come back to 100% charge. So what we usually do in design is that batteries, depending on the brand, on the type of battery, whether lead acid or lithium ion battery or whatever type of battery, there are usually specified depths of discharge. And for many of the battery, it's written on the data sheet. So for most lead acid battery, it has 50% depth of discharge. So what 50% depth of discharge means that if it contains 100 units of energy, it cannot give you that 100 units. It can only give you 50 and hold back 50. Okay, it cannot give you more than 50. That's what it means. For lithium ion battery, they can give you as much as 80 and hold back maybe like 20. So that's what depth of discharge means. So you also have to take that into consideration. So when you're sizing your battery, you have to know that what you need is 12,000 watt hours. So you're not sizing a battery for 12,000 watt hours. If you size the battery for 12,000 watt hours and you're using lead acid battery, I'm sorry, it can only give you 50% of it, which is 6,000. Okay, and then you find out that you have done a wrong design. Okay, so when you're designing, you have to take account into the depth of discharge. Typically for lead acid battery, it is 50%, like I said. So the battery size will not be given by this. So your battery size will not become the usable capacity in terms of kilowatt hour. Okay, so the battery size will become the usable capacity in terms of the watt hour divided by the depth of discharge in percentage. Okay, so for in our own case now, this is our own design now, our usable capacity that we want to get from this battery is 12,000 kilowatts hour. Sorry, that should be watt hour. Okay. So please, this is what I'm going to make the correction and then send you the updated version. Okay, there's a mistake here. So well, our usable capacity is 12,000 watts hour. Okay, so we're going to divide it by our depth of discharge, which is 50%. 50 over 100 will give you 0.5, right? So that's 50%. When you divide it, you're going to have 24,000 watts hour. That's the battery size that we need to design for. So if we design for 24,000 watt hours, then that 24,000, that battery capacity can only give us 50% of that capacity, which is what we actually need, the 12,000 watt hour. Okay. If you have a different depth of discharge, so if you have 70% depth of discharge, all you need to do is to divide this 12,000 watt hour by 0.7, and then you get something else here. Okay. So batteries are usually rated in voltage represented by V and amp hour. If you look at your data sheet for your batteries, what you're going to see is that it is rated in voltage, the voltage of the battery, and you're going to see the amp hour. Even your phone, your mobile phone batteries are rated this way. Okay. So for you to determine the amount of energy it can hold, you remember that energy is watt hour. That is power times time. Okay. So we go back to our formula of power, which is power is equal to voltage times amperage. Okay. Voltage times amperage is your apparent power, not your real power. For you to get your real power, you have to multiply by a power factor. And that's why you can see I have in faint color power factor, but here we are neglecting the power factor. I just have to put this so that you become aware that when you have voltage times current, what you're having is apparent power. That is, this shouldn't be watts, it should be VA. This should be VA. But the moment you multiply with power factor, then it transforms into watts. Okay. So, but let us neglect this power factor and assume that this is in watts. That's the whole essence. So now remember that our energy is power times time. Now this is our power, voltage times amperage. This is power, voltage times amperage, then times time. Okay. So when you now do that, you have watts hour, right? So now this current times time, which is this two thing here, is represented by amp hour in your battery rating. This amp is your current, then your time. That's what this amp hour that you're seeing, that's what it means. So current times time is equal to amp hour. So let us replace this IT in our energy equation. So what you're going to have is voltage times amp hour, right? So when you want to calculate the amount of energy that a battery contains, so you just need to multiply the voltage that is given in the data sheet times the amp hour that you're also given. Okay, so like I said here, P means power, E means energy, voltage means V, then I is current, then AH is amp hour. I hope this is clear. I'm just trying to explain to you how to be able to determine the energy content of any battery. Given the characteristics in volts and amp hour, we can determine the amount of energy it can hold. We'll solve an example so that this becomes very clear. So here is an example. Calculate the number of batteries required to produce 4 kilowatts hour. If you want to change it to watts, watt hour, it becomes 4,000, but we are talking about 4 kilowatt hour here, which is the same thing with what we had in our assessment. It's the same thing as 4,000 watt hour, only that here we've converted it to kilowatt hour. So calculate the number of batteries required to produce 4 kilowatt hour of daily energy need, plus 3 days of autonomy for cloudy / non-sunny days, using lead acid battery with the following ratings: 12 volts, 200 amp hour, and 50% depth of discharge. Okay, so we need to calculate the number of battery that we're going to need to produce this amount of energy. Okay, so let's see what the solution. So here is how we solve it. Our daily energy need is 4 kilowatt. That's what the question is asking of. That's our daily energy need. Okay. But again, it's not telling us that it needs a 3 days of autonomy. So we multiply that for that energy need for 1 day times 3 days. So we have 12. So for 3 days, that facility is going to need 12 kilowatt hour to function, assuming there is no sun. So now the actual battery size at 50% depth of discharge is, remember in our formula, I shared the formula how to calculate the battery size given a certain depth of discharge. So we are not going to divide this 12 kilowatt hour by 50%, which is 0.5. When we do that division, we are going to have 24 kilowatt hour. So our battery size has to be 24 kilowatt hour, so that this at 50% depth of discharge, this 24 kilowatt hour can give us 12 kilowatt hour, which is what we need for 3 days. Okay. So now, specific storage capacity of the battery, that is for a single battery of this characteristics, 12 volts, 200 amp hour. So specific storage capacity of battery is 12 volts times 200 amp hour. I explained this in the previous slide. That will give us 2,400 watt hour, or 2.4 kilowatt hour. One battery can hold this. So how many batteries do you need to get this? It's just a simple division. we divide this 12, sorry, 24, not 12. We are looking at the amount of battery that we're going to need to give to be able to store 24 kilowatt hour. Then out of this 24 kilowatt hour, it can give us 12 that we need to power our appliances for 3 days. So all we need to do is to divide 24 by the specific storage capacity of the battery, which is 2.4 kilowatt hour. So once we do that, we're going to have 10 batteries. So we need 10 battery of this capacity. We need 10 12 volts battery and 200 amp hour to be able to support those load for 3 days. Okay. I hope that is clear enough. So we have to solve an example here. There's an exercise. Can we just please try our hands on this exercise and see what we'll get? If you've gotten the answer, you can unmute your mic and speak, or you drop your answer in the chat box. Has anyone arrived at an answer?
This was the daily energy this thing.
Sorry?
The daily energy required.
Energy need.
It's 4 kilowatts. We are still looking at 4 kilowatts.
Okay, because it was indicated.
Yeah, we are still solving for this example that I gave, but again, we're not assuming that the battery characteristics has changed. You have 12 volt battery with 100 amp hour, and the depth of discharge is 80%. And in this case, we are using a lithium ion battery, not lead acid battery. So that's the exercise that you're supposed to solve, not for lead acid battery.
I got 12.5.
3.5.
12.5.
4.2.
Sorry?
4.2.
Okay. 4.2. Someone got 3 points. What? 5. Okay, approximately 4. Okay. So Jackson said is approximately 4 batteries. Then Peter said 4 pieces of battery. I need more. So 2 people has responded. Okay. Janus said 4. Is anyone having challenge in solving this? If you're having challenge, please let us know, because I want everyone to be familiar with this. The purpose of this is not just for you to be here. It's also for you to be able to design this system. If someone calls you to design a system for him or her, you should be able to do the calculation and tell him the number of battery that they need, give him the characteristics of the battery, then talk about the inverters, talk about the solar panel. I mean, you should be able to do all of that's the essence of this training. So if you're having challenges in doing this calculation, please speak up. Let us know what your challenge is and we can be able to solve it. So a good number of people are saying 4. Yes, you're correct. It's 4.2, then approximately 4 if you do the theoretical approximation. Okay, yeah. So that's what the answer you should get. However, instead of scaling down, it's always advisable that you scale up. So maybe you can just do 5. Okay. So, but theoretically, by your calculation, it is 4.2, and you're all correct. So let's proceed.
Okay, 4.2. I got it. 4.2.
Okay, all right.
I got it now. 4.2.
Okay. Good. So now let us look at the sizing of the PV array. Okay. So using the previous load details and data from the previous example. Okay. Of course, our required PV energy output is 24,000 watt hour. We all remember that the battery capacity that we need to support is 24,000 watt hour. Okay, that's from the load assessment that we did. Okay, so just to remind us of that. So the energy that we need the PV capacity to support is 4,000 watts hour. Okay, so how we go about that, we have to now determine what the peak sun hour is for that location. Like I said, peak sun hour is location dependent. Okay, so if we know what the peak sun hour is, okay, then all we need to do is to divide the required energy output by that peak sun hour, and it's just a straightforward calculation. And then we'll have what the PV size would be. So our required load that we need to support is 24,000 watt hour. If you divide that by 6 hours for Nigeria as an example, in Nigeria it's basically 6 hours, but it depends. Some location might be 5 hours or less. So it all depends. So on the average, we use about 6 hours for Nigeria. So if you divide that 24,000 watt hour by 6 hours of peak sunshine, what you're going to have is 4,000 watts. So you need a 4,000 watt PV array to be able to produce 24,000 watt hour in a single day, assuming you have a peak sun hour of 6. I hope it's clear. So, but this is theoretical. This is theoretical at standard test condition. So if you go and buy a solar panel of 4,000 watt hour, there is no guarantee that you get 4,000 watt hour, because the rating of the 4,000 watt hour is at standard test condition, and the condition you're deploying those solar PV is not at the standard test condition. It could be worse. It could be a condition that is less than the standard test condition, and therefore you should expect a lesser performance. Okay, so how do we now? Jackson, you have a question?
Yes, sir.
Please go ahead.
The PV size we achieved, these are 4,000 watts. Have you considered the battery charging? Is battery charging factored into this as well?
So what we need, remember that the battery that we need to charge a battery up to 24,000 watts hour. That's what we are sizing the PV for. Is that clear?
Okay, yeah, I'm with you. You know, at
So
normal
we are looking for,
operations in
okay, go ahead.
normal
Go ahead.
operations in a home, while the battery is charging, the loads will still be used. My madam
Yes.
will be watching TV, and all other things. So, can you be comprehensive enough so that we can digest it? Thank you.
Yes, very well. Like I said, there's no one size fits all. It all depends on the configuration and what your clients want. Okay, and that is why it is very important that we understand how to calculate all of this, so that if the parameters changes, you know how to also change them in your own calculation. Now, in this case, in this example that we are doing, the assumption is that this solar panel is going to charge the batteries, and from the batteries, it's now going to be discharged by the inverters and they supplied to the facility. Okay. Now, if you're designing for a system whereby the solar PV system has to be charging the battery and also supplying energy to that house, mind you that there is it's in rare cases that you're going to have 100% energy supply from that solar PV because of fluctuation. So in some cases, whereby the sun intensity is not so high, then energy will also be drawn from the battery to compensate what is coming out from the PV to supply to the facility. But in cases where now the PV system has sufficient energy power to supply the home and then charge the battery at the same time, then your load entirely will now be on the PV system. Then the excess energy will now go to charging the battery. So if that is the case, which is what you're asking now, whereby you're now using the energy directly from the PV and also being able to charge the battery, in that case, you now have to now modify the amount of watt hour that you need. So instead of 24 watt hour, you're not going to consider the amount of load that PV system is going to be powering, right? The PV system is going to be powering your load and then charging this battery up to 24 watt hour in a day. I don't know if that is clear, Jackson.
Yes, I'm following you.
Yeah. So I take that again. This is you need to charge this battery fully for 1 day, and again, you want to be using the energy from those PV arrays directly in your house. Okay. So what that means is that your PV size will have to increase. That's what it means. But again, you have to ask yourself, is it really necessary, since you've taken care of all your load demand in this 24,000 watt hour? So those are the questions you ask yourself. So if you want to do that, if you want to use that PV directly, maybe you might say, okay, let me scale down my battery storage. Okay, so that the battery storage can only last you only a night's time, not for the whole day, but just only a night. And so in that case, you have to now calculate the amount of energy that you need only at night time. Okay, but the overall rule here is that you need to estimate the amount of energy that you need in watt hour, whether you're using it in real time or you're using it as a storage. If you determine that, just divide it by your peak time hour, then you get your PV size. Is that clear? Daniel, you can go ahead and ask your question.
Yes, it's clear.
Okay, thank you. So let us proceed. So when we do our division, what we have is 4,000 watt hour of solar PV array that we need to be able to generate 24,000 watt hour with 6 hours peak sunshine every day. Okay. Is someone still raising his hand? Daniel, are you still raising your hand? Okay, I guess that was previous one. Daniel, do you have something to say?
I want to ask, let's assume we are still using this example we are using 24,000 watt hours.
Okay.
I want my battery to be charged. At the same time, I want to use my PVs immediately. Okay. Can I make a design of, let's say, 26,000 watt per hour, so that I'll be able to use the 24 and use the other two to
Now,
charge.
let me tell you how you can come at that. If you want to get this 24,000 watt hour as a battery storage, so the question is, what is your load is 255 watts, right? Assuming you are using this example now, right? So you want to be charging and you want to be using that load of 255 at the same time, okay? So the question you're going to ask yourself is that, okay, if I use that load of 255 for 6 hours, right? That's for these 6 hours that the sun is going to be out. So times that 255 by 6. Let me just do that. 255 times 6. So you have 1,530 watts. So add 1,530 to this 24,000 watts. Then you divide by 6. Then you see arrive at something higher. You arrive at something higher than this.
Okay. Okay. Thanks.
Okay. Can you please mute yourself now?
Okay.
Okay, so now this is our PV size at standard test condition. But again, the actual PV size that we're going to need, we are going to divide this 4,000 watt hour by performance ratio. So our PV performance ratio, it depends. So you could use 80. So in this our example, let us assume that performance ratio is 80%. Okay, so if out of the 100% of what they've told us that this PV can generate, which is 4,000, we are going to, it can only give us 80% of this 4,000, okay? But we want it such a way that it should still be able to support us with the generation of 24,000 watt hour. So what we are going to do, we are going to divide our PV size at standard test condition with the performance ratio. So when we do that, we are going to get a higher solar array size, which is 5,000 watts. So our solar array size will have to be 5,000 watts for us to be able to generate 24,000 watt hour energy with 6 hours of peak sunshine, assuming our performance ratio is 80%. Are you seeing how all of this thing is coming together to determine what your PV array size would be? So if we all understand this, then let's do exercise number 3. So it's now asking you to calculate the actual PV size if peak sun hour is 5 and performance ratio is 65. So please, let's see. You can try this out and let's see what you get. If you have an answer, you can unmute yourself and then speak.
Please, I didn't get the question.
So the question is now asking you to calculate the actual PV size of this our example, assuming that the peak sun hour is now 5 instead of 6, and your performance ratio is now 65 instead of 80% that we use. What would then be your PV size? Oluwatosin is asking how to get the performance ratio. I discussed about that yesterday. Your performance ratio is actually your theoretical output from the PV, which is stated at the data sheet of your PV, you have to divide it by the actual measurement. So you have to actually measure what the PV is producing when you installed it. Then when you divide that, then you get what your performance ratio should be. So Peter has posted an answer. Okay. Benson has also posted an answer. I need more people. Daniel, Jackson. Jackson, did you get 7.384 or 7,384? What did you post? Are you putting your answer in kilowatt or watts?
No, 7,300. It's a comma, not point, sorry.
Is it? Okay.
7,384 point.
Okay, we have to be careful with.
It's actually
I actually got
7,384.6.
Okay.
I also got 7,384.6 watts.
Okay. So we're all correct.
Okay.
Yeah.
Thank you.
Yeah. So we are all correct. That will be the size of the PV that we'll need. If the peak sun hour has dropped to 5 and our performance ratio has dropped to 65, then what that means that we'll actually need a higher PV array to be able to give us this same load. Okay. So you can now see that you can see how these things affect the size of your system. Your performance ratio has a way of affecting the size of your design. Your peak sun hour has a way of, so all of these things comes together to affect your actual PV design or the size. So it's good we understand how to play around with all of these formulas and parameters. So good. So now let's come to the sizing of the solar charge controller. Now the solar charge controller is, please mute yourself. If everyone should mute.
Hello, Chima.
Okay, Uche.
Maybe you didn't just finish up with, as we got 4,000, there's no PV in market that's 4,000. So maybe.
Okay.
Get the lowest minimum, yeah.
So when you say you mean 4,000 watts?
Yes, I mean, how many number of PV? Assuming they are buying to 200 or 50.
Okay.
I know you assume they already know, but you never can tell.
Okay. Thank you very much for that. So what Uche has just pointed out now, so our required PV size here is 5,000 watts. Okay. So what that means that if you go to the market, if you now have 300 watts PV, how many are you then going to need? So all you need to do is to divide 5,000 watts over 300. Then you get the number of PV that you need. So for the example the exercise that you solved, that you got 7,384.6, then of course you need to mark it up to maybe 7,005. Since sometimes, this PV is actually cheap this time around, only that the battery is very, very, unfortunately, very expensive. Okay. So Jackson, you have a question?
Yes, sir.
Go ahead.
So, well, if you divide it like that, how do you achieve if they will be in series or if they will be in parallel? How many will be in series and how many will be in parallel to achieve your voltage and the current you want?
So I'm coming about the current when I will discuss about the charge controller, but about the voltage, it all depends on the voltage. Now, this PV systems has voltage ratings. When you look at the data sheet, you will see the voltage, the output voltage, open circuit, you will see VOC, open circuit voltage, okay, on those PV systems. That's what you're going to see. So it now depends on what you're connecting to. What voltage battery are you, or what voltage of battery are you want to charge? Okay. So that will now determine how you'll be able to connect them. So for example, if you have if your PV system, if your PV model is 12 volts, okay, and then you're using a battery of 24 volts. So what that means is that you need to connect that PV model you need to connect two of them in series. Okay, so 12 plus 12 will give you 24, right? So you need to connect two of them in series to get 24 volts. Okay. Then after that, if you need to increase your amperage, you don't connect them in series anymore. Rather, you connect them in. So you have two PV modules connected in series. Then you can now have maybe about 6 of them, 6 of the series connected in parallel. Is that clear? Jackson, you asked the question, right?
Yes. It's clear.
Okay.
I understand.
Okay, so good. Daniel, you have a question?
Yes, can you please come with the explanation? I didn't get it right.
Sorry, Daniel, I can barely hear you.
Can you please come with that explanation? I didn't get you right.
Okay, now, I said this yesterday, so I want to elaborate. Let me elaborate further on it about series and parallel connection. If you connect PV modules in series, you will increase your voltage. If you connect PV, if you have 12 volts, the output voltage will be 24 volts. If you add another one, you're going to have 36, I think so. Yeah, you have 36 volts, which should be, so assuming that you need 24 volts, but you're using a 24 volt battery, you want to charge your 24 volt battery, okay? Therefore, you cannot connect 3 of them in series. You can only connect 2 in series to achieve your 24 volts. Then you cannot connect, if for example, you have 6 PV modules that you want to connect, 6 of them, and each of them is 12 volts. You will connect 2 in series, 2 in series, 2 in series. So you have 3 series connection, right? Then you connect those 3 series, you connect them in parallel. If you connect them in parallel, your voltage will now remain 24, but your amperage will now increase. Daniel.
Yeah, I get it now.
You get it now? Okay. So what I'm going to do, maybe by tomorrow, I'll just put just a slide to explain this further. I know I talked about it yesterday and I'm talking about it today. So it tells me that it needs further clarification. So tomorrow I'm going to put up just a slide to explain this configuration, okay? So just to make it, to drive home the points further. So we are talking about solar charge controller in this case now, okay? So using the same sample load details that we have and the data from our previous example, you can still recall that the energy that we need with 3 days autonomy is 24,000 watts hour. And our battery voltage here is 12, okay? And our PV module array is 5,000 watts. These are all what we have already established. These are all what we already know. So we want a solar charge controller that will be able to charge this battery capacity using this capacity of PV module. So how do we determine that? So required solar charge controller is equal to solar PV size, this is our solar PV size, divided by your battery voltage. I take that again. Your required solar charge controller is equal to your solar PV size, that is this solar PV array size, divided by your battery voltage. So if your battery voltage is 24, then you're dividing by 24. If your battery voltage is 2, then you're dividing by 2. Now your solar charge controller is measured in amperes. It's measured in amperes, okay? So if you look at this formula, if you break up this watts, you know this watt is equal to voltage times current. So this voltage will cancel that voltage that is here. So the remaining idea is ampere. So your charge controller is rated in amperage. So if you divide 5,000 watts by 12 volts, which is our battery voltage here, you'll be able to get, so required solar charge controller will now be 416.67 amperes, assuming other losses are neglected. Of course, you know there will be losses as the current moves from the solar panels to the charge controller. So let us just neglect all those minor losses. So now this is the size of solar charge controller that you need to charge those batteries that can store up to this amount of energy using this size of solar panels. So so you have to know that increasing the battery voltage will reduce the capacity of the charge controller required to charge the battery. So if assuming you have 2 volts, I've seen projects where they use 2 volts battery, and the idea is pretty simple. Remember that power is equals to voltage times current. So if you reduce your voltage, you actually increasing your current. So for them, for those kind of people, they actually want to have more amperage. Then they can have those two volt battery. They have to connect them in series. They connect 6 of them in series. Assuming they want 12 volts, they have to connect 6 of them in series to still get 12 volts. Okay, so just to do a little bit of deviation and explain that. So, but the point I'm trying to make here is that if you reduce the voltage of your battery, okay, then you actually increase the size of your solar charge controller. Okay, so if you use a higher voltage for your battery, then your charge controller will use a lesser capacity than to work. So just so that you know how this thing relates to each other. Jackson, you have a question? Hello, Jackson, you raised your hand. If you are speaking, then you have to unmute yourself to speak. Otherwise, we'll just continue. Okay, so let's continue. If at the point you're ready to ask, you can always ask your question. So this is how we determine our solar charge controller that is required to charge this capacity of battery with this capacity of solar PV array. So in summary, 416.67 amperes charge controller is required to support 5,000 watts solar PV array to charge 24,000 watt-hour battery storage. You see how everything has now come together to tell you what your design will look like. You know what your solar PV array would be. You know what your charge controller capacity will be. You know what your battery storage will be, and you know what your PV, your inverter would be in the first slide when we started. So let's have another exercise here. So this is now asking us to calculate the required charge controller for the previous exercise that you did. You remember the previous exercise you did, you got 7,384.6 watts. So using that wattage now, okay, so that's the previous exercise. So calculate the required charge controller for exercise number 3, assuming that the battery voltage this time is 24, not 12. Assuming that 24 volt batteries were used. So let's you can try that out and then unmute yourself to speak, or you can post your answer in the chat box.
I think it's 208.
You got 208. Let other people.
307.6.
307.7. Okay.
0.6.
Okay. 0.6. Okay. Almost the same thing with Peter. Who else has gotten an answer? Okay.
307.7 or 0.6. Okay.
Okay. Okay. Okay. Okay. So is anyone having difficulty in doing this? The first person said 208. I don't know. Have you been able to get it right? Let me know. If you have a challenge, please speak up. I didn't capture the name of the person that spoke, but I want to be sure that he has gotten it right. Is anyone having challenge doing this calculation? Okay, so I take that to be that all of us got it correct, and that's the answer, 307.69. So if you approximate it, 667. But we should also take into consideration that you cannot go to the market and then see the charge control of 307.69. So you have to approximate to the nearest highest value, just for tolerance.
Excuse me, please. I can't enter the chat room.
You can't what?
I said I can't type in the chat.
What could be the proof? Is there any speaking?
Confirm.
Please, I think
Someone's voice, Jackson, are you speaking? Your voice is blurred.
Mr. Chima, I said I can't type in the chat room. Mine.
Yes, I heard you, and you said you can't type in the chat box. I don't know where the problem could be coming from. But
can you try press alternate key and H together? Maybe you're not seeing the chat icon.
And did you hear that someone is suggesting that you press alternate? Can you say that again?
Alternate button, Alt plus H. Alt plus H.
Okay. And can you please try that and then see if it works?
It's back now.
Okay, good.
Without pressing anything.
Okay.
sorry, before we proceed, sir.
Okay.
Hello, can you hear me?
I can hear you, please. Go ahead.
The last exercise,
Okay.
were we using 5,000 watts?
No.
I think that's what did we use?
You're using the result of your previous exercise, which is 7,384.6 watts.
Okay.
Yes, that is the problem here, because it was not very clear. Because if you use 5,000 watts and you divide it by
24,
you will have 208.
Okay. So sorry about that. I know I said that when I was reading out the exercise. I said that you're using the answer that you get from your previous exercise. And it's written there. The answer you got from your exercise number 3. Okay.
I cannot even move the slide back.
307.69.
Okay.
Yes, I can only see what you are, I can't take it backwards.
Okay.
So thank you very much. Using 7,384.6 divided by 4 actually gives 307.69.
Exactly, correct.
Yeah, thank you very much.
Okay, so let's proceed.
All right.
So like I was saying, you cannot go to the market and then find a charge control of 307.69. So it's always advisable that you mark it up to some certain level. Okay, so if you go to the market and you find a charge controller of 400 or 450, then it becomes suitable. But don't go less. You don't go less, you go higher. Okay, so just for safety margins and tolerance levels and all of that. So, but theoretically, this is how you know the exact charge control that you require. Then you then mark it up for tolerance and then safety margin. So that's a very good one from all of you. I mean, the exercise has been very well successful so far. So now let's move ahead. We are going to discuss the concept of penetration rates. Now, the reason why we are talking about penetration rates here is that in many times when you're designing solar PV systems, in many cases, you might need to have to integrate it with some other power sources for them to become viable. So for example, you might need to integrate it with generator. Okay, in some cases where you don't want to do a battery storage because, like I said, unfortunately, battery is very, very expensive. In fact, it is a major factor why solar PV system has not uh, gotten up to the market level where it should at this time because of storage. Once you're able to achieve a breakthrough in storage, I mean, you're going to see a very radical uptake of the system, whether wind or solar. But for now, the problem that we are having is the storage, which is still very expensive, painfully very expensive. So instead of going for storage, it's always more economical to integrate your solar PV design with generators, which is what I want to talk about. That's the next section I want to talk about now. Okay, how you combine your solar PV design with other sources of energy. So when you're combining with other sources of energy, then your penetration rates becomes important. Okay. So there are two important parameters that needs to be kept in mind when sizing a hybrid system. Remember, I said you're combining with other sources of energy, and when you're doing that, what you're actually doing is a hybrid system, right? So now, two of the important parameters are: one, the penetration rate of the solar power; two, energy share in production between solar power and diesel generator, assuming you're combining with a diesel generator. Okay. Now, these two concepts should not be mixed up. They are interrelated, but not the same. Penetration rates can be static or dynamic. Now, let me give a little bit explanation on this penetration rate, both the penetration rate and energy share. Penetration rate has to do with power. So that's why I highlighted it. That's why I made it bold here. Penetration rate has to deal with power. Energy share deals with energy. Power and energy are not the same. I keep saying this. So that's just the difference between penetration rate and energy share. So now, talking about the penetration rate, there are two types of penetration rates. You have static penetration rate and you have dynamic penetration rate. So let us talk about static penetration rate. Static penetration rate is defined as a ratio between installed PV power and diesel generator apparent power. Apparent power is kVA or VA, that's apparent power. And you remember that your generators are rated in kVA. Okay, so if you have, okay, so for an example, a hybrid system of 950 kilowatts peak of PV and a total diesel genset power of 1,600 kVA, that is, you have 4 generators of 400 kVA. If you put them together, 4 times 400, you have 1,600 kVA. We have a static penetration rate of 59.3 as shown below. Before we show this below, let me just explain, because that below has some decimal point that might be confusing. Okay, so if you have a total power demand of maybe 10 kVA, okay, so and then you have a solar panel of 4, okay, now let me say 10 watts, 10 kilowatts, sorry. That's your demand. Then you have a solar panel that is installed solar panel of 4 kilowatts. Okay. So your penetration rate will now be, ideally, your penetration rate here will be 40%. Okay, because you have 10 units of demand that is in kilowatts, and 4 of that is being supplied by your solar system, right? So if you check the percent, the rate, the percentage, the energy, not energy share this time. If you check the power that is being supplied by the solar system out of the 10, then you're going to get 40%, and that's what penetration rate is all about. So I have to come back to this example. I wanted something that is simpler to explain that. So in this our example, you have a static penetration, which is penetration static is equals to, this is your peak capacity of your PV system divided, forget about all of this, forget all this formula that you're seeing, What this simply means is that is your total generator capacity. Okay, that's what it means. So your peak capacity of your PV system divided by the total installed generator capacity. That will give you what your PV penetration rate is actually. So what we actually have here is that in this example, you have 950 kilowatt peak of installed PV system as given here. You now divide it by the total generator size, which is 4 times 400. That will now give you 1,600 kVA. If you do this division, you are going to have 59.3%. So what that means that 950 is representing 59.3% of this total capacity. Okay, so that's what it means. That's what your penetration rate is. Okay. So now we are talking about static penetration. Static penetration is talking about your installed solar PV. Mind you that installed solar PV is not the same thing as its energy yield or energy or power output. Power output varies at all times. If your power output from this 950 kilowatt peak solar PV system in the morning is not the same thing in the afternoon, and it's not the same thing in the evening. So it varies. Okay. So in systems with low static penetration rates, that is up to 20%, a controller is usually not needed as critical system state will not be reached. For most common load profile, in other words, the PV output of less than 20% will always be within the limit of a base load. I wish I have a load profile here to illustrate this. So what this is talking about is, if you have a total energy demand of 1,600 kVA that normally your generator is supposed to take care of, okay? And you want to integrate your PV system into this generator. Remember, I did some illustration yesterday where I talked about the load profile and I talked about how you can match your solar PV profile with your daily energy demand profile. Now, what this is saying is this. What this explanation is saying is this. If your penetration rate is less than 20%, okay, then you don't need a controller because all that the PV system is going to generate can always sufficiently be taken care of by the base load of the facility. So if the base load of the facility, for example, in this case now, if the base load of the facility is, okay, now, this is 1,004, 20% of 1,006. 20% of 1,006 will give us 320 kVA. So if you install a PV system of 320 with this generator, okay, what is saying that your base load almost at any time, the consumption from this generator will be more than 320. That's what it's saying. Whether in the morning or in the evening or in the afternoon, your base load is your minimum consumption on your load profile. Not just your minimum, but again, your minimum consumption over a certain period of time is usually an average, okay? So, but in actual sense, if you have a PV system that is installed and combined with this generator, and it is not more than 320, you don't need a control. But if it goes more than 320, the chances is that there will be a time when your PV system will be generating more energy than your demand can take. And mind you, in this case, there is no storage. And you're running generator at the same time. So if that happens, then there will be a problem. In that case, you're going to need a controller to solve that problem. That's what I'm trying to explain here. So in more complex system with penetration rate above 20%, a controller is a must. Now, all of this, there is a simulation I'm going to do down somewhere in this presentation that will explain all of this, that will make it very clear. So let's talk about dynamic penetration rate. A dynamic penetration rate is defined as the ratio of actual PV to the total load at a certain point in time during an operation. Remember that I said that you have a PV of 950 kilowatt peak does not necessarily mean that at every point you're generating this. No. At every point, you most likely going to be generating less. So your actual generation at any point in time is what we now refer to as your dynamic penetration rate. So it's different. It's different from morning, it's different from afternoon, it's different from evening. So here is the formula. For example, a PV is generating 472 kilowatts, while the total load is 727 kilowatts, making the dynamic penetration rate of 64.9%. But at another point in time, it could be different. Like I said, it could be different in the morning, in the afternoon, in the evening. So here is the formula for calculating the dynamic penetration rate. So you're not measuring the actual output from your PV system. Mind you, you may have a 1,000 kilowatt peak of a PV system, but at the moment, what is it generating? If it's generating 472, then that's what you use for your dynamic penetration rate. Whereas in your static penetration rate, if you installed 1,000 kilowatt peak PV system, then you use 1,000. But for dynamic, you use what is actually generating at the moment. So if you use that, you now divide it by the total demand at that time, not the total installed capacity of a generator, but your total demand at that time. For your static penetration, you're using the actual installed PV divided by the total installed generator capacity. But in your dynamic penetration rate, you're now dividing with your actual output for your solar PV divided by your actual demand. So when you do that, you have 64.9% at 11:15 hours. So at 12 o'clock hour, it could be different. At 13 o'clock, it could be different. At 18 o'clock, which is that's at 6 o'clock, it could be different. So that's what dynamic penetration is. So other definitions are possible, and one should always check which definition is used in the specific case. So some other people might have a different definition. It is possible, but this is the basic and most commonly used definition. So let's talk about energy share now. We'll talk about penetration rates. Let us talk about energy share. From an economic point of view, I don't know if we should take a break now. I think we've spent over 1 hour, 30 minutes. Should we take 10 minutes break and then come back at less than 10 minutes? Let's come back.
Yes, no, not less than 10 minutes, please.
Okay,
10 minutes, 10 okay.
10 minutes break. Okay, so let's
not less.
Okay, so let's do 10 minutes break and we'll come back at okay, let's come back at 3:50.
4:50.
4:50 rather, sorry. So let us come back at 4:50, then I will continue from energy share. All right, so your break starts now. So before the short break, I was talking about energy share. I just finished talking about penetration rate, and I talked about static and dynamic penetration rates. And before then, we talked about the sizing of the solar systems and all of that. And I just want to chip in that I hope you all know why we need charge controller. Charge controller, when I talked about charge controller, we did the calculation for charge controller. I just thought I should show this brief explanation that charge controller is actually required to control the charging of the battery so that the battery is somehow delicate equipment so it doesn't overcharge and then maybe spoil before its useful life. So you need a charge controller to regulate the current that goes into the charging of the battery from the solar modules, and that's why you need that charge controller. So having said that, let us continue with the energy share. So from an economic point of view, another parameter much more important than penetration rate is the energy share. Now, to determine the energy share of the different type of generators, the final energy production of the PV system and final energy production of the diesel generator are compared. So in this case, you're not talking about, when we talk about the penetration rate, we are talking about the installed capacity, we are talking about the actual power generation in kilowatts, okay? But in terms of energy share, we're actually looking at the actual energy that was generated from the PV, and you're comparing that with the actual energy that was generated from the generator. You put two of them side to side, you can ask, okay, this is the share of energy from the PV system. So for example, if a hybrid PV diesel system produces 10 megawatt hour of electrical energy, and two of those 10 megawatts come from the PV system, thus the energy share of the PV system is 20%. This is straightforward. You have 10 megawatts and 2 megawatts is coming from PV system. So 2 megawatts of 20 megawatts is 20%. Pay attention that we are talking about energy. You see megawatt hour, sorry, I think I keep saying megawatt. Megawatt hour, not megawatt, megawatt hour. Okay. So compare the figures, that is parameter on sunny days. Okay, this is on the next slide I'm going to share, but I'll just read this out. Compare the figures, parameter on sunny day and parameters on cloudy day. That is on the following page. They show the difference between penetration rate and energy share on a sunny and on a cloudy day. Now, with a static penetration rate of 40%, the solar energy system contributes an assumed 8% and 28% respectively of overall produced electrical energy. In order to calculate the energy share, the squares in the diagram has to be counted. Now, this is the diagram we're talking about, and I'm going to explain that here, so you don't worry. The statistics that you saw here are already represented. This 8%, 28%, 40%, they're already represented here. So I'm going to illustrate all of that here. So now this is PV penetration and energy share on a sunny day. We'll look at the situation on a cloudy day, but this is on a sunny day. So in order to calculate the energy share, the squares in the diagram have to be counted. Like I did explain yesterday that, look, the peak demand of this profile is 110 kilowatts. That's the peak load, right? The boxes inside this profile, each one of the box represents the energy. Each one of the box represents 1 kilowatt hour. Okay, so if you want to calculate the energy share, now the yellow part is the part of the solar PV. If you want to determine the energy share for this profile, you count all these boxes that are in yellow, then you count all these boxes that are in ash color, then you divide the number of boxes in yellow divided by the total boxes, both the one in yellow and the one in gray. You divide.
Jinashima, sorry, let me pause you. Somebody is like an NL got locked out. She can't log in again. She just called me. So I don't know. Check the waiting room.
Just
I hope there's no problem, because if it's a mistake, she might not be able to log in again.
Let me see if there's anybody in the waiting room.
Then Solomon Oyebude, I don't know, you can chat. I sent you a chat. Can you reply me, please? Solomon and who again? Otronye. Just pardon me, okay? Otoni. You can't see her.
I can't find her in the waiting room.
That's a big problem. Maybe there's a problem, and once this thing happens, she might not be able to log in again, because it's based on registration. I don't know.
Can she use another system?
That's
I don't
what
know,
I'm saying.
or use a different Zoom account.
Okay, but just be on lookout. Let me call her. Just be on lookout in case.
If she can use another Zoom account to log in, I mean, that will be fine. There must be a way out. Okay.
Let me inform her. Okay, so Otonye, Nko, Taria, and Solomon Oyebo, they just chat me up. I've sent you a chat. Well, thank you. Continue, please.
Okay. So like I was explaining about the energy share in this figure that we have here. If you want to determine the energy share, I think I need to move everybody now. So the energy share here, you have to count the number of squares that are on the yellow color. Then you divide it by the total number of squares, inclusive of the one in ash and the ones in yellow. When you divide it, that will now give you the dynamic, okay, this penetration rate. It will now give you this energy share of 28%. Okay, if you take your time and count all of these squares, you now count the squares in yellow, and then you divide it by the total number of squares, you're going to get 28%. And that tells you the energy share from the solar PV system. Okay, and then of course the rest of the energy is coming from the generator. So this is energy share. Now let us look at, like I said earlier, that the peak demand for this facility is 110 kilowatts. That's the peak demand. But then the real peak of the solar PV system is 60 kilowatts. That's the peak that the solar system can give you, 60 kilowatts. Okay. Now the installed capacity, this installed solar system capacity is 80 kilowatts at standard test condition. However, it's only generating 60 kilowatts. Okay. And of course, I said the real system peak demand is 110. So now, based on this peak demand that we've highlighted here, okay, one more thing. We have an rated power of the diesel generator to be 160 kilowatts or 200 kVA. 200 kVA is an apparent power, while 160 kilowatts is the real power. So the difference is the power factor. If you apply your power factor, you can convert between the real and apparent power. So that is the installed generator capacity in this facility. So based on all of this, we can now be able to determine what our static penetration rate is. Remember, I said static penetration rate has to do with your installed solar capacity, which is 80 kilowatts, divided by your installed generator capacity, which is 200 kVA. Now, installed generator capacity is apparent power, not 160. You're now talking about the kVA, which is the apparent power. And remember, we are talking about static penetration, not dynamic penetration. We are talking about static penetration. You're talking about installed capacities. Your installed solar PV capacity is 80 kilowatts, as can be seen here. Your installed generator capacity is 200 kVA, as can be seen here. So when you now do the division, you're going to have 40%. So your installed static penetration here is 40%. So for your solar system contributes 40% of your total installed capacity. So that's static penetration being illustrated here. Now let us look at dynamic penetration. So despite the fact that you have 80 kilowatt peak of the solar system, but what it is actually generating at the peak period, at this time between 12 noon and 2 p.m., what it is actually generating is 60 kilowatts. And that's what we're going to use to calculate our dynamic penetration at that time. So you have 60 kilowatts divided by the actual peak load. Now look at the peak load, 110. Okay, so the peak load here is 110. So when you divide it by the actual peak load, which is 110 kilowatts, you have 55% dynamic penetration rate. Okay, so that is the difference between static penetration rate and dynamic penetration rate. This dynamic penetration rate is for 12 noon. It's for this 12 noon. The dynamic penetration rate, Okay, NA is now here. Okay, good, great. So please, I want us to do a little exercise on dynamic penetration rate. What would be the dynamic penetration rate at 10 a.m.? I need to admit some people, but you can go ahead and start solving that. So the question I asked, what will be the dynamic penetration rate at 10 a.m.? The value here, the solar output at that time is 40. The solar output at 10 a.m. is 40. So what will be the dynamic rate? Is this just a straight ahead calculation? And then you have your peak demand at that time at your 10 a.m. is still the same thing as 110. What do we have?
36.36%.
36.3.
Okay. So that's correct. So that's how we determine the dynamic penetration rate and the static penetration rate, and of course the energy share. Now this is for a sunny day. Let us look at what the situation is. So let us see what it is on a cloudy day. So PV penetration and energy share on a cloudy day. So on a cloudy day, you can see that your solar system is performing very low. However, your static penetration did not change. I don't know if you've noticed that, because your static penetration is static. As the name implies, it is static, it doesn't change. It's about your installed capacity. So, but what would have changed is your dynamic penetration. So still at 12 noon, remember we have 55% on a sunny day, but on a cloudy day, the same time at 12 noon, what do we have? We had 18%, because your solar yield, your solar energy at that time is just 20, and you're dividing by the demand, 110, you have 18%. So in this case now, you can now see that your energy share for a cloudy day, if you count this box here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, it's about 14, but you have to divide it by the entire box here. You have to count the entire box here. So 14 divided by an entire box here, you're going to get 8%. If you divide it times it by 100, you get 8%. Okay, so your energy share on a cloudy day is low. So that tells you that even if you have a very large solar PV installation, on a cloudy day, the performance will be low. So therefore, when the performance is low, you need another source of energy, another source of power to be able to power your equipment or your load. So that power can either come from a generator or from battery. And like I said, battery is very expensive. So if you're designing a larger facility, sometimes it's always good to have a backup generator instead of battery. However, if your clients can afford the battery, then fine and good. You can go ahead and install the battery. So if that is the case, you must be able to take care of the solar module that will be able to take care of charging of those batteries for cloudy days or for days of autonomy, so that on the days of autonomy, the battery can be able to stand up and then serve the load. So let us look at generator minimum loading. And this is important because it plays a significant role in the control of your solar PV system. When you integrate your solar PV with generator, then generator minimum loading kicks in. It has a lot of role to play. So, Otonya, you have a question? You raised your hand.
Yes, sir. I have a quick question, sir. Could you go back to the last slide? Yes, I was a little bit confused here. The dynamic penetration rate here in the red box circle here, It's 20 kilowatts divided by 110 kilowatts. That gives you about 18%.
Exactly.
Correct?
Yes, correct.
Okay, here now, the energy share for the solar is 8%.
Correct.
Okay, so the other one here, the other one in gray is 92%. That is the peak
The
demand.
energy share from the generator.
The energy share from the, okay, yeah, that is the difference between the solar and the generator.
Out of 100% energy requirement for a whole day, for this whole
Correct.
day, yes, solar system only supplies 10% of the energy, while generator supplies 92% of the energy.
Okay, that's 8% and 92%.
Correct.
Okay. You also talked about counting the yellow boxes. Correct. And dividing it by the one that is in gray. If you do that, it's not going to give you 18.
No, you're not just the one in gray. You're both the one in gray plus the one in yellow.
In yellow.
Yeah, both of them combined.
Okay,
Yeah,
as your what? As your
total energy for that day.
Okay, which is 110, right?
No, 110 is your power, is your demand, not your energy.
Right.
So your energy is, you need to, so I said that every of these box, assume that every one of these box represents 1 kilowatt hour.
Right.
Yeah, so if you count all of these box, inclusive of the yellow one, okay, and you divide the number of box in yellow by the total number of boxes you have here, you will get 8%.
8%.
Yes.
Okay. Okay. Fair enough.
Are you okay? Okay. Are you clear now?
Yeah.
Okay.
Thank you.
Okay. You're welcome. So let's proceed. Talking about generator minimum loading, and I try to explain why it is important. When you combine your solar PV with your generator, now let me read what I have here so I don't repeat myself. It is important to note that every diesel generator has a certain minimum loading. It is usually expressed as a percentage of its power generation capacity and is generally provided by the manufacturer. Typically, diesel generators should be loaded at a minimum of 30% of rated power. This is because running an engine under a light load might lead to damage. A situation could occur in which the available PV power combined with the minimum loading of the diesel generator exceed the current load. There are two options to handle this situation. Now, the situation is this. Your generator has a minimum load that it is required to function. Now, we've said it is 30% of the rated power. Okay, so if you have 100 kilowatts output from a generator, okay, that is the rated power output. Active power this time, not apparent power. It is expected that at least 30 kilowatts, that generator should be serving a minimum load of 30 kilowatts at all times. It shouldn't go below 30 kilowatts. So now the situation, what happens if your solar system is generating, so you have 100 kilowatt load to power, and your solar system is generating 80 kilowatts, meaning that your generator should not power the remaining 20 kilowatts, right? But this is not telling you that no, your generator has a minimum loading. It must be 30%. So you can see that there's a problem now because your solar system is not generating more, and your generator cannot go below 30%. So so that's the situation. And it's not telling us there are two options to handle the situation. One of the options is the PV inverter can be derated to produce less power than possible. So with the example that I cited now, you have 100 kilowatt load to power. your PV system is generating 80, but your generator cannot do less than 30. So your generator still have to do at 30%. So your PV system has to derate itself and produce 70%. So the 10% will not be wasted. Only 70% can go into your system. That is one. Two, another way to handle this is, or the surplus energy could be stored and utilized later when the load increases or when no PV power is available. So another way to do this, if you integrate a storage system, instead of that 10% being wasted, you cannot store it in a battery storage system that you cannot use at other times. So those are the two ways to handle this. When you're doing a hybrid system, you must make sure that the system requirements for both the generator and the solar system are fulfilled. But again, there has to be a priority because the generator is a mechanical device. And again, it's like I said, it has a minimum operational requirement that must be met. So when this kind of situation arises, you just have to sacrifice some output from your solar system to fulfill this minimum requirement. So the second option would introduce storage into the system, making it more complex and costly. Like I said, battery is expensive. So let us now look at our example, integrating this minimum load now. So the figure shows an example with a minimum loading of 30% of the maximum load of a diesel generator. That is 50 kilowatts. So the generator we have here is 160 output kilowatt active power. So if you take 30% of it, you're going to get 50 kilowatts. So at all time, this generator must be powering a 50 kilowatt load. Now, a storage system is not included. Now, the red color that you see shows the cases when PV power generation has to be derated. Derated means that you have to curtail it. That's what it means. So now let us look at this. At 8 a.m., okay, your total power is only 60. Your total power at that time is 60. But again, your solar system is generating 20, meaning that your generator can only take 1, 2, 3, 4, 40, right? Not at 8 a.m. Yes, your generator can only take 40 because your solar system is generating 20. But again, the condition has stated that your generator cannot perform below 50. So what that means that you have to now derate your solar system so that your generator can take 50. So in this case now, if you count this box that are stacked up, we take it that every one of these boxes, of course, when you trace it down to this y-axis, it's 10 kilowatts. It's 10 kilowatts interval. Okay, so we are talking about 8 a.m. So this is 1, 2, 3, 4. So this is 40 kilowatts, which violates the condition we want that generator to operate. So we have to derate this solar system so that the solar system can only produce only 10. And the generator can now run at 50 kilowatts load. So that's what it means. That's what it means to derate your solar PV system when you're combining it with your generator. Now let us look at what happened at 1 p.m. At 1 p.m., your demand dropped to 110. No, is that 110? Okay. Your demand drops to 100. So once your demand drops to 100, you can now see that your generator is now beginning to power less than 50. So you have 10, 20, 30, 40. Your generator is left with 40. So at this point again, you have to derate your solar system. So your generator can now power 50 kilowatt load, while your solar system powers the remaining 50 kilowatt, in as much as your solar system is producing 60 kilowatts. But because of the minimum loading condition of a generator, we cannot use all of that. So that's what that's how you derate your solar system when you're combining with the generator, and you have to fulfill certain minimum operating condition of the generator. Otherwise, you run a lot of inefficiencies in your system, and the generator might even break down sooner than you think. So now let us look at different setup, between generator and solar system. So we're going to look at the categories of PV diesel hybrid system. Now, these systems basically suitable for mini grids. If you're doing a project for if you're developing a mini grid project, then it's highly suitable. If you're also developing for a larger facility, maybe a commercial facility, then it is suitable. Basically, for home systems, you can just do your little battery support, little battery storage. That might be fine. It's more economical when you're not designing for a larger facility and you want to integrate your solar system with your diesel generator. It makes more sense. So PV diesel hybrid systems can be designed in very different ways. The figure that you're looking at gives an overview of different configuration of PV diesel hybrid systems, ranging from a purely diesel powered system, 100% diesel, to a purely solar powered system. So look at the transition. At this point, you have 100% diesel at this very point now. So all your load are powered by diesel. But as you begin to move along to the right path, you can now see that this yellow part is your solar. So when you begin to integrate your solar, at this point, you just integrate a little amount of solar to your generator without storage. At this point, there's no storage yet, okay? Because whatever the solar can generate, your base load can always take that. Let me explain this base load here. I wanted to explain it before. Okay, so if you look at this load profile, now this is a load profile, right? Now your base load is this portion. 50 kilowatts downward is your base load. So you can notice that at any point in time, you're consuming 50. At any point in time, you're consuming 50, and that's what base load means. So if you have a solar system that is within this range, then you don't have a problem. I think I said this yesterday. But if your solar system begins to exceed your base load, especially during the afternoon time, then you need a controller. So this is what base load means. So now what I was trying to say that is you can see that when you begin to integrate your solar system here, you find out that whatever the solar system can produce can easily be taken up by your base load. So you don't need any controller. But when you begin to increase your solar system, at this point, 1B, you increase your solar system. At this point, it's still very okay. It's still within your base load. But as you keep increasing that, you get a point where you now begin to exceed your base load. So this two scenario now, you're now beginning to exceed your base load. So what happened is that the excess that is going to now come out from that solar system, what do you do with it? In this case, you have to install a battery storage system so that the excess can be installed in a battery. Okay. So as you keep increasing the penetration of your solar system, you have to keep increasing your battery storage, because as you keep increasing the penetration of your solar system, you have more energy during the afternoon that you cannot use, and you need somewhere to store it. So you have to now begin to increase your battery capacity up to the point where you now eliminate your diesel generator and you have a large battery bank. This is a large battery bank, so that during the day, the solar system is producing enough energy to charge all of this battery that you can use at your night time. So in this case, this is purely solar PV system without diesel generator. Whereas you started with 100% diesel generator, you ended up with 100% solar PV system. So your design somehow will fall somewhere along this path. But for the purpose of this training, we are going to focus on A1. We're going to focus on this A1 category, where your solar installation does not exceed your base load. So okay, I've done that. The brown and yellow area represents the energy share in the system. The brown is equal to energy from the diesel generator. I already said that. The yellow represents energy from the PV system. The category O is given to the 100% diesel system, as this cannot be considered in hybrid system. Of course, if you're running only diesel hybrid, only diesel system, it's not a hybrid system. It's a purely diesel generator system. If you're running 100% solar system, it's not a hybrid system. You're running purely 100% solar system. But if you now begin to move anywhere between here and this point, then you now have this is where you now have a hybrid system. In between is where you have a hybrid system. Okay, so by introducing more and more PV and more complex components into the system, fuel consumption and emissions are reduced. Now, as you begin to integrate more of solar system, if you begin to increase the penetration of solar system, of course, you begin to reduce the emissions from your diesel generator, and you begin to save money to some extent. So with 100% PV system, there is no fuel consumption and there is no emission. So this training will focus on category 1, like I said, which means that a PV system is added to the diesel generator, but no storage system is applied. This means that PV power only replaces power from the diesel generator when the sun is shining. So in a 100% PV system, fuel consumption and emission are at maximum. It is simple solution for off-grid electrification with known disadvantage, high fuel cost and high maintenance cost. Now, this is talking about 100%. If you're running 100% diesel system, you of course you're going to spend a lot in maintaining the generator. You're going to spend a lot in fuel. So, but with the connection of a small PV system, the diesel generator is supplemented and fuel can be saved. If you begin to integrate solar system, you begin to reduce the demand from that generator. And when you begin to reduce the demand from that generator, the fuel consumption will begin to reduce. And mind you that solar systems are cheap and they have a very long lifespan of 25 years. So the PV system is then connected directly via an inverter to the diesel generator. For larger PV systems with static penetration rates between roughly 20 and 60%, controller has to be integrated. Again, the penetration rate is not equal to the fuel saving. Fuel saving for setups with up to 60% static penetration ratio are usually around 20 to 25%. So if you have a solar system, if you have a penetration rate of up to 60%, okay, you're most likely going to have a saving in terms of your energy cost. You're going to have a saving around 20 to 25%. So higher static penetration rates, thus higher PV energy share can only be reached by integrating storage into the system. Since there is still no other grid forming device beside the generator, at least one generator still has to run at all times. Now, I'm going to explain this because it is very important. You know that your solar PV system is not reliable because of the intermittency of the sun. And sometimes shadow might cast on the PV system. So imagine that you have your solar, assuming that your energy requirement is 50, okay, 50 kilowatts. And then your solar system is generating 60, for example. You have a solar system that is generating 60 kilowatts. And then, of course, it has to be rated so that it can produce only 50 that you need. But you now begin to imagine what happens if a shadow suddenly casts on that solar panel. Assuming your generator is not running, you're 100% depending on that solar system. And suddenly there's a shadow on that PV model. What's going to happen? Your system will collapse. Your appliances will go off because there is no enough power to sustain your equipment. So for this reason, it is recommended that your generator must be running. Even though you're using your solar panel, your generator must be running so that if there's a shadow on the solar panel and there's production from your solar panel drops, your generator can quickly pick up the load and then keep powering your system. That's what it's trying to say, that since there is still no other grid forming devices besides the generator, at least one generator still has to run at all times. Now, if we push the solar energy share up to 100%, all energy demand is covered by the solar system, and no diesel generator is needed. However, please note that reaching 100% leads to disproportionate increase of the system size. This happens because we have to cover the entire volatility of the solar resource, and more solar panels. Of course, we have to cover the entire volatility of the solar resource with more solar panels, especially more storage. Therefore, in large systems, it is usually more economical to keep a generator in the system as a backup source for a period of low irradiation. I've explained this before, that because of the high cost of storage system, battery storage system, it's more economical to keep generator as a backup. Now, if you want to do without generator, some of the mini grid that we have in Nigeria does not have generator as a backup. They have battery as a backup. But now this is the problem. You're going to have a disproportionate increase in system size because you want to make sure that at every point in time, the load is, I mean, your battery storage capacity and the solar system is able to meet whatever load that is going to be placed on that system. Now, here is the problem. For most of the time, the load might be small. And then you now oversize your system because you want 100% reliability. It becomes a big problem. You now have oversized system. I have so many redundancy. It becomes a problem. That's why it is advisable that you size your system appropriately. However, it's advisable that it's more economical to have a diesel generator as a backup, as opposed to having an excessive storage capacity. And some of the early mini grids that were developed in Nigeria, study that were conducted shows this study was conducted by the RMI, Rocky Mountain Institute. It's a US-based organization in Nigeria. Now, most of these mini grid, the early mini grid that were developed in Nigeria, many of them were performing at a very low utilization factor. Some of them were performing at a utilization factor of about 20%. So you build a system that can perform at 100%, and for most of the time, it is performing at 20%. So you have a large excess capacity that is lying idle, not being utilized. So some of those systems were over-designed, but it's a learning curve. Like I said, this is our first set of mini grids that were developed in Nigeria. And as we keep doing this, and we keep learning and we keep improving. And that's why it's very important that we understand all of these terminologies and parameters. Okay. And let me just add that those mini grids that I talk about, most of them does not have diesel generator backup. They are purely PV storage system. So now let's talk about adding storage. Energy storage incorporated in PV diesel hybrid systems can have several functions or purposes. Most commonly, a storage system is used to control the power quality, that is the voltage, frequency, and reactive power. You can also use the storage to provide additional spinning reserve, as well as to avoid the rating of the PV's output by shifting produced solar energy to later hours of use. You can also use the storage system to reduce maximum loading of a generator. So at some point, when your generator, the demand from your generator is at its peak, you can release some of this from getting to its peak demand, or even from overshooting its actual capacity. So these are one of the many reasons why you can have storage added to your designs. Now, the spinning reserve is something that we're going to talk about in the simulation that we're going to do. Now, spinning reserve means that when you're running your generator, have you thought about why it is important that you don't run your generator at 100% of its capacity? When you have, for example, okay, the generator that we have here, we have 200 kVA generator, and then the output is 160 kilowatts. It is not ideal for you to put a load of 160 kilowatts on that generator. Now, the reason is if there's any additional increase. So, for example, if somebody now add additional load, what happens? Then the system will most likely collapse because you're not adding excess capacity to that generator. So, for this reason, we need every power system needs what we call spinning reserve. Whether you're designing a solar system or whether you're running a generator, even the power, the NEPA, the PACN that we have today, they all have spinning reserve. So that if there's sudden increase in load, you can easily accommodate it. That's what spinning reserve means. So a storage unit has to be able to provide electric power within seconds. It should have a high cycle efficiency and a low discharge rate. The following table shows a brief overview of some available storage technology used in PV diesel hybrid system. someone was asking me about the DOD of lithium, a kind of a battery. I don't know, I can't remember, but I know I saw that in the chat box. So here are some specifications of battery with different characteristics. So you have the lead acid battery, you have the lithium ion battery, you have the redox flow. Okay. So now here are the properties. The lead acid battery, like I said, it has a maximum daily DOD of 50%. For lithium, is around 80%. Whereas for this redox flow, this is not common. It has 100% DOD, meaning that you can discharge it 100% and then recharge it again, and nothing is going to happen. It even have a cycle of 10,000 life cycle. Whereas the lead acid has a life cycle of 5,000, the lithium ion has a life cycle of 4,000. This cycles means that the number of times you can charge and discharge these batteries before they begin before they begin to fail. They have 85% cycle efficiency. So out of the 100% energy that it's supposed to give you, not 100% of energy that is stored in the system, but out of the energy that this battery, lead acid battery is supposed to give you, you're only going to achieve 85% of it. So 15% of it will go as a loss in terms of extracting that energy. That's what it means. So for lithium ion battery, you have 95% cycle efficiency, whereas the redox flow, you have 75%. So these are basically the characteristics of different categories of battery. You have the lead acid, lithium ion, and then redox flow. They have their advantages, they have their disadvantages. You can read them up. So this is just an example of a battery storage bank. So what you can see here, these are lithium ion batteries, whereas these are lead acid batteries. So let us do a simulation of a dynamic PV diesel hybrid system. I hope that by the time we're done with this simulation, most of all I have said today will become very clear. So we have a system. So in this example, the system has the following characteristics. The maximum load is 800 kilowatts. That's the maximum load. The maximum load is, this is 800 kilowatts. So this is the maximum load, 800 kilowatts. So the minimum load here is 500 kilowatts. This is 500 kilowatts. The minimum load is somewhere here. So PV nominal capacity is 1,200. So installed PV capacity is 1,200 kilowatts peak. So we have three diesel generators, each with a maximum power output of 320, which provides a total available power of 960. When you times 320 times 3, you have a 960 kilowatts output. So this 960, so this system can actually run only on diesel generator because your maximum output is, your maximum load is 800. It can as well run 100% on solar system because you have 1,200 kilowatts peak. But in this case, it's a hybrid system. We are combining both of them because we want to save money. We want to reduce diesel consumption. So now here are the technical requirements for this system. You must maintain a minimum spinning reserve of, the spinning reserve of the genset must be greater than 5%. So please, can someone just punch a calculator and tell us what 5% of 320 would be? That's for one of the generators. So for every one of the generators that we are running, we must maintain a minimum spinning reserve of 5%. So 5% of it, this capacity must be reserved. We must not exceed it. So someone just help us check what 5% of this will be while I proceed. So minimum operational load. 16. 16. Okay. Thank you. So at every point
should be 1.6.
No. 5% of 320.
20. Okay, 16.
Okay, thank you. So please mute yourself now.
Yeah, it's actually 16.
Okay, so thank you. So now, part of the requirement that minimum operational load per genset is 30%. So the generator set must not, at any point in time, power less than 30% of its power output, of its of its capacity. Remember I said that each of the generator capacity is 320. So at no time must it power less than 30% of this capacity. Please, someone should check what is 30% of 320. So at least 2 gensets must run in times of load greater than 320 kilowatts. There is no storage in this
96.
system. There is no grid connection. Okay, 96. So at all time, the load on the generator must not go below 96 kilowatts. That's what it means. And for this system, there is no storage. It is not connected to the grid. Our only source of power is the PV system and the generator. So let us see how we can combine both of them and power this entire load profile from 00 o'clock up to 24 o'clock. So let me quickly describe what we have here. So look at the graphs here. This part that you're seeing, the yellow part, is it actually yellow? But this part that you're seeing is the PV generation profile. This is the PV generation profile. Now, this part that you're seeing here is the load profile. All these parts are the load profile. Then remember we have three generators of we have 4 generators. 1, 2, 3, 4. How many generators do we have? Sorry.
3.
Yeah, but I think it should be 4 generators. Sorry, it's actually 4 generators. So you have 1, 2, 3, 4 generators. Okay. I'm going to make that correction, and then in the final slide that I'm going to send to you. So these are the nominal capacity of the generators. They are all 320 kilowatts. So now this bar that you're seeing here, this bars that you're seeing here will actually represent the actual generation of the generators. So this is generator 1, generator 2, generator 3, generator 4. Now this is the total generator capacity. So it's a combination of what all of the generators are producing is going to fuel this bar. Whereas this is the this bar here is for the PV system. So I just want to walk us through this platform before we start the simulation. So note, the slide shows the monitoring system that will be used in this slideshow. In the upper part of it, you can see I've explained all of this already. So let's just go ahead. So now this is 1 a.m. Look at the time here. This is 1 a.m. That's at night. There is no sun available. Okay. Thus, the diesel generators provide all necessary power to the load, which is 559.3 kilowatts. So this is 1 a.m. The load at this time is 559 kilowatts. Now the 3 generators operate at, you can see that 3 generators are operating. 1, 2, 3. They are all operating at 186.4 kilowatts.
Sorry, Engineer Chima, please, is it 3 or 4 generators? I'm becoming confused here.
Sorry, I said it is 4 generators. I will make that correction and then send the final slide to you.
So is 4 generators operating at 186.4 kilowatts?
No, all of the 4 of the generators are not run. Okay, I understand where your confusion is coming from. Now we have 4 generators installed. Okay, we have 4 generators installed, but not 4 of them are running. Now the reason why we have 4 of them is depending on our load. Certain number of generators will come. There will come a time when we have only 2 generators operating. I don't know if you understand, but we have 4 generators installed. So at this time, at 1 a.m., we only have 3 generators running. 1 of them is idle. And is that clear?
Yes, I understand you better.
Okay, thank you. So we have 4 generators installed, but at 1 a.m., we have only 3 generators running because we have a total load of 559.3 kilowatt load that we need to power. So 3 generators are operating at this time, and the three of them are operating at 183.4 kilowatts. So each of them is operating at 58% of their rated capacity. Okay. So if you look now, you see that these three generators are operating at 58%, and they are producing a total power of 559.3. At this time, there is no sun, so only generator is running. That is 1 a.m. So let us see what happens at 2 a.m. Now this is 2 a.m. The load is slightly decreasing, so the generator also reduced their electricity output to 178.3 kilowatt each, which corresponds to 56%. They were running at 58%, but now they're running at 56% because there is a drop in demand. Okay, so the PV set point is not relevant at night because it will be, of course, it will be explained later. There is no solar generation at this time, so it's all running on generator. So now it is 3 a.m. Now we see that just after 2 a.m., the third generator was switched off, and the two other diesel generators had to increase their power output in order to cover demand. Now, at this time, what is the demand? They produce now 258.5 kilowatts, which is 81. Diesel generator in operation, which is currently not used. Moreover, the efficiency of the diesel generator increases with its load. So switching from 3 to 2 generators saves fuel. I hope we understand what happened here. Because the power demand keeps dropping, it gets to a point where 2 generators can easily handle the demand, and 1 generator goes off. And the moment this generator goes off, the load that it was powering was transferred to this other 2 generators, and their capacity now increased. Their load factor now increased to 81%. They were operating at 56%. But the moment they pick up the load from this third generator, their load capacity increased to 81%. Okay. So we only have 2 generators running now. Remember that we have 4 generators installed, but only 2 generators are running at this moment. So now this is 4 a.m. Now the rest of the night, the two generators, I think there is a slight misinterpretation here. I think it's from Zoom also. So the 2 generators supply the electricity. That is generator 1 and 2. They supply the electricity. Now the load does not fluctuate in this simulation. Thus, the diesel gen sets can operate in a stable manner. Now, if you notice that at 4 a.m., the load is really kind of stable here. So 2 generators keep operating. But you notice that the load has also dropped a little bit. So our load factor has also dropped from 81 to 79%. So this 2 generator is still very okay to carry the load. At 4 a.m., nothing much has changed. The 2 generators are still operating at 78%. So now let's see what happened at 6 a.m. Now the sun is rising and the PV system started to generate electricity. Its current feed-in is 24.3 kilowatts. You can see that there is a small yellow portion here, which is this 24.3 kilowatts. Now this generator could therefore reduce their power output slightly, since power of the load is covered from the PV system. So this little power that has the PV system has contributed is a small penetration. We reduce the demand from the generator. So the generator will now come down to 74 load factor. If you see now, the solar system is generating 24, while the generator is producing 74, the 2 generators. At 7 a.m., the PV system generates 160 kilowatt, which is 13% of the nominal capacity. Now the penetration rate is now 31%. So the penetration rate of the PV system is now beginning to increase. So it's now generating 160.5 kilowatts, and the penetration rate now is 31%, while the generator is now doing 69%. So you can see how the penetration rate of the PV is beginning to increase from 7 a.m. Now this is 8 a.m. The sun rises further, and PV generation from power generation from the PV system and the PV penetration rate increases further. Now there is even more PV power covering the load than power from the diesel generator. This load is increasing steadily now, but not as fast as PV power generation. Now you can see that this is the load, okay? But this is what the PV system is powering. So the remaining load here is being powered by the generator. Now what he's saying that from this point, you can see that the load is beginning to increase very fast, okay? Because it is morning time and a lot of activities are beginning to happen. So you cannot see that our two generators are still running, and both of them are running at 33%. Now I want you to ask yourself, if you combine these two, don't you think that one generator could have powered, don't you think that one generator could have taken care of this demand from these two generators? Because if you combine 33 plus 33, it will still give you 66, which is not even up to 70% of one generator. Why do we still have to run two generators? Can someone make an attempt to explain why we still have to run two generators at 33%? They are near their minimum loading. Whereas one generator could have been running. If one generator is running, their load factor will be, the load factor of these two generators combined with 66, right? One generator could have done the work. So why do we have to run these two generators?
For tolerance.
Okay, so it is for reliability. Remember when I said, so assuming that one generator is running, now look at the total demand. Here. Now the total demand here is 569. Assuming one generator is running, remember that one generator is what? 320, right? And there's a shadow cast on this solar system. This one generator cannot carry this load. I don't know if you understand. If there's a shadow cast on this solar system, if the solar system goes off suddenly, okay, this one, if you assume you have only one generator running, it cannot power this 569.9 kilowatt load. That's why you need these two generators. So if anything happens to this solar system because of its intermittency, its unreliability, if there's a shadow or somebody blocks it and the power supply for this solar panel drops, you have enough capacity from these two generators to take care of this demand. And that's why you have two generators running, just for the sake of reliability. Does that make sense? Somebody raised hand. You can go ahead and ask your question. If you have a question. Otoye, you have a question? Jackson, do you have a question? If you have a question, please unmute your mic and ask. Otherwise, I will just lower the hands. Okay, I take it that their question has been taken care of by the explanation.
Can you hear me now?
Okay, I can hear you, Jackson.
Okay, I raised the hand. I have a question, sir. It
Okay,
goes
please.
like this. When doing load sharing, because it seems I've lost the little way I've seen it, I think from the DB, you isolate the load that you don't want on your inverter, put them on your other lines. Like call it, you dedicate line 1 for inverter, and you dedicate line 2, line 3 for other loads. So as you are saying, if generator or inverter suddenly goes off, the generator will need to take over the remaining loads. Does it mean that you go to the DB and put on all the, or start disconnecting and connecting again to the generator line? Let me understand that, please. Or is it handled by the charge controller?
Now, there's a control, there's an automatic control system that does this control. It determines the load that is the system needs to power, and then it's able to combine the generation sources to meet that load, depending on the criteria or the condition that you're giving to it. Now, in this system, we did not do any load isolation. All the load in this facility are being powered by the combination of diesel PV hybrid system. And we want to achieve 100% reliability. So assuming that this is a factory, they don't want interruption. They are running their production system. They don't want interruption, okay? You cannot run uninterrupted factory operation on the grid system, on the NEPA system, because they can fail at any time. So some of the factories that we have in Nigeria, in fact, when they want to run the operation, they switch off from NEPA, they on their generator. Why do they do that? Because they want 100% reliability. They don't want an interruption. So that is the system we are trying to simulate here. There is no load isolation here. You're not going to your DB to isolate any load, okay? So the load that needs to be powered, so does that explain it now?
Yes, I'm following. Wow, that's
okay.
Let me ask. So the answer to his question is simply that there is a special controller that senses all the power supplies and then kind of switches up some and puts back some on in order to just achieve the required load.
Okay, yes, that's exactly what it is. There's a very popular technology, SMA. If you're conversant with the renewable energy industry, you would have heard about it. SMA is a German technology. It's a smart controller that does all of this work. It senses, it senses the demand, what you need, and it automatically controls which power generator comes on, the number of generators that comes on, the amount of power that comes from the grid, assuming you're connected to the grid. I mean, it does all of those controls.
Oh, okay.
Yeah, exactly.
Okay, thank you.
Okay, so we assume that you have a very sophisticated controller in this simulation that actually controls. So it knows that there's no way. I mean, because it knows that the power supply from your solar system can reduce at any time. So you must have enough spinning reserve plus reserve capacity to take on the load that are coming on from the solar system, should in case they fail at any time. Because of the intermittency of the sun can decide to drop, and the amperage from the sun will drop, and your power output will drop. So if you don't have enough reserve capacity to take on that load, then your system will fail. Okay. So what we're simulating here is for 100% reliability. We don't want any failure at any point in time, and that's why you have two generators running. Otherwise, one generator could just run. But the problem here is that if you're running one generator, which is 320 kilowatts, and you're powering a load of 569 kilowatts, and there's a shadow cast on this solar system, and the power now drops. Within seconds, before this generator could come up, a lot of systems would have been damaged. A lot of things could damage. So you need these two generators to be running so that if there is a shadow, if there is a reduction in production from the solar system, the two capacity combined, which is going to give you 640, is greater than this. It can take care of this at any time. That's why you have two generators running. And this is 8 a.m. So now 8:30 a.m. Just after 8 a.m., a special situation occurred. Now the power output from the system had to be limited below its actual power output potential. This was necessary because the power output from the two operating diesel generators was already reduced to their minimum load level of 30% operated power. It could not be reduced any further since excess electricity cannot be stored in any system. The PV power output had to be readjusted according to the load level. Now look at what happened. remember that at this point, the two diesel generators were running at 33%. So they're getting close to their minimum performance, minimum load requirement. And they eventually get to that point. Okay. So even though your solar system is now producing more power, okay, now the solar system is producing more power. That when you combine with the output from this generator, will now exceed your actual demand, which is 591. So what I'm saying, if you combine the energy output from your solar system plus 30% output from these two generators, it will exceed what you need. So at this point, your output from your solar system have to be derated. Okay, it has to be derated, and that's what this is trying to say here. That the PV output has to be adjusted according to the load level. So at this point, there's no way this generator can perform below 30%, because that is the standard set condition that has been given to it. If one of them were to be running, the same thing that I explained earlier, if one of them were to be running, it cannot meet this demand if there's any interruption on the solar system. So two of them must be running to cover up for this capacity. So let us see what happens at 9 a.m. So at 9 a.m., then the third generator was switched on again, also supplying electricity at its minimum load level of 30%. This was necessary due to the spinning reserve requirement, which is determined by the load level and a security margin due to the increase of diesel power. The PV power output had to be reduced in order to avoid excess power generation. Now, for the same reason that I explained before, this third generation has to come on, and the generator came on and it's operating at its minimum requirement. Now, see what the problem. If you keep running only these two generators at this their minimum requirement, the capacity of these two generators is what? 640, right? Remember that we need to have a more than 5% spinning reserve, which is 16. Okay, so 640 plus 16 plus 16, that is 32. If you add 640 plus 32, 640 plus 32, it's going to give you 672 kilowatts. Okay. So if you, assuming you have only these two generators running, sorry, that is going to give you 672 kilowatts. Okay. No, sorry, I made a mistake. It's actually 640 minus 32. Not plus 32. 640 minus, you must have it as a spinning reserve, as unused capacity. So you're minusing that 32 from the actual capacity. So you're going to have 608. Okay. So when you now see that, okay, the maximum power that you can get from these two generators is 608. You now find that it is less than your demand here. Your demand is 628, but the output from these two generators is 608. So if there's anything wrong with this solar system, these two generators can no longer meet this demand. And that's why the third generator has to come up. I'm trying to explain to you why this third generator has to come up. So at every point in time, you must make sure that you have a generator capacity that can meet your demand. However, those generator capacity can function at their minimum load requirements. I hope that is clear. So if you combine the capacity of these three generators, they exceed your total requirement. So should in case if your solar system goes off, your system can still function with these three generators. This three generators will just pick up the demand that is being supplied by the solar system. And that's the reason why your solar system has to be derated at this point, at 9 a.m., so that these three generators can function at their minimum load requirements. So now we keep moving. We can see that the demand is now increasing, and the solar penetration is now also beginning to increase again. It was 28% here. Now it has increased to 33% because any additional energy that needs to be supplied has to come from the solar, since these generators are already operating at their minimum load requirements. Okay. So at 11 a.m., with increasing load, the PV power output and the penetration rate are also increasing. So you see that the penetration rate keeps on increasing, 36%. And we have to keep looking at our total generator capacity that is running. We have to keep comparing it to the demand at any point in time. If at any point in time we find out that this demand is going to exceed this generator, the fourth generator will just kick in. That's what the automatic control does for you. So let us see what happens at 12. So at 12 noon, the demand from the solar is increased. It has reached 40% penetration rate now. At 1 p.m., it keeps on increasing. Now, all these three generators are still operating at their minimum load, so that whatever is coming out from your solar system has to be feeding into the system. In as much as it is somehow also reduced, somehow derated, but okay, it's not derated at this time. It was derated at this very point. And from this point, any other generation was fed into the demand. So at 12 p.m., the PV power output suddenly dropped sharply. Sharply for a few minutes, only producing half of the power as before. Now, thanks to the spinning reserve of the diesel generators, they can increase their power output immediately up to 189.3% kilowatts. Now, each of them is operating at 59% of rated power in order to ensure that the supply of the load is not interrupted. Now, the reason of the drop in PV power output could be as a result of a passing cloud or other shading effect. So it could be there was a shading effect on the PV system and the power suddenly drops. Okay, so you can now see that the generator quickly ramp up their output. They were operating at 30% minimum capacity because the solar was, providing more of the energy. But at this point, the supply from the solar just suddenly drops, and then the generator quickly pick up the demand from the solar system, and everything keeps running smoothly. The people who are using this power wouldn't know what is happening here because the automatic control is taking care of all of these things, right? So now you have three generators that are operating at 59% of their rated power. The solar power has suddenly dropped to 21%. So let's see what happens again. So at 3 p.m., after the interruption, the system operates as before. So at 3 p.m., the solar system starts operating as normal again. And you can see now that the penetration has now increased to 65%, while the generator is producing 35%, right? And they have now reverted back to their minimum load requirements. So at 4 p.m., now the load starts to decline. You can see that the load has gotten to the peak and it begins to decline at this point. Now the PV penetration rate at 3 p.m. and 4 p.m. is the highest with 65%. So this is the highest penetration rate that we've seen at 65%. Okay, so from this point on, the PV will now begin to drop, as well as the load will begin to drop. So at 5 p.m., now due to limited solar irradiation, the diesel generators have to increase their power output after 4 p.m. because the power output from the PV system decreases. Now you'll notice that the PV system is now beginning to decrease. So the diesel generator has to begin to increase. They have to begin to pick up the load from the solar system, right? So let's see what happens again. So as the sun keeps going down, the generators keeps increasing their capacities. Now the generators are running at 72% of their capacity, while the solar has now reduced to 15%. Now something happens here. So at 7 p.m., just after 6 p.m., the reserve generator 4 is switched on. Again, this is due to the required spinning reserve of the diesel generators. Now the load is almost fully supported by the diesel. So at this point, you can now see that their load here is, the total load here is 811. That's the total load here, 811. And if you combine these three generators, with the spinning reserve, you take away the spinning reserve, it's going to be less than this. So you need additional generator to be able to meet this load. And that's why the fourth generator came on board. And they are all operating at 62%. That's 4 of the generators are operating at 62%. Now the solar system penetration rate has actually almost died down at this point, almost tending to 0. So at 8 p.m., there's no more sun. Okay. So the reserve generator capacity only operated for short a while. At 8 p.m., it is switched off again. Now you find out that the total load capacity has dropped. It was 811 here, which was the reason why this one has to come on to be able to support this load. But now it has dropped to 788. So this 3 generator can now carry this demand. And that's why this one now went off again. And this 3 generator can actually support this load at 100%. So at 10 p.m., the load keeps on decreasing. So you have 3 generators still running. The load has decreased to 685. Okay, it keeps decreasing to 636. At 12 a.m., it's now, the load has now decreased to 613, and you have 3 generators running, and at a load factor of 64%, each of them. So this is the entire system from 12 a.m. to 12 p.m. This is how the automatic control works. It senses how your demand is changing, and it automatically controls the supply sources, the number of generators, and the penetration rate of your PV system. Okay, so the whole idea is to maximize what is coming out from your PV system, so that you have a less consumption of diesel, and by less consumption of diesel, you actually save money. So that is the whole essence of this simulation, or the whole essence of integrating your PV system with your diesel generator. So this is how a PV diesel hybrid system works. So I think this is the last slide of this simulation, where you now have at 12 a.m. This was almost the point where we started. So that is it for today. Sorry for overshooting our time. This is a few minutes past 6 o'clock. I thank you all for your active participation in this training for today. We have one more day to go. That is tomorrow. Tomorrow, I will take you on. I will take part of the time to walk you through cost estimation of solar PV system, so you can actually know how to cost some of these systems. And then I think I will introduce you to the PV software. It's a simulation software that can also help you determine the energy yield, the tilt, and so many of these things that you ordinarily have to do calculate manually. So that's the whole essence of some of this software. In as much as the software is going to help you do some of this, and you still have to